So, welcome to lecture number 9 in network security. Last time we started with network steganography, and this is the skill of hiding information in some plain sight, in some kind of regular data that is not suspicious. So the model is typically you have some kind of covert sender who wants to hide the communication, so wants to hide the information that is transferred, and some receiver, and the goal is to communicate over some regular data access that looks normal but contains some hidden message. So the assumption is that there's always some kind of supervision, that somebody is looking into the data and tries to identify patterns and the secret. So the main approach for steganography is then on the, let's say, attacker side, or the persons who want to hide the information, to agree out of bounds by some other means, by some other channels, on some kind of pattern, some kind of positions where the information will be hidden, and then to put the information in these pieces and to receive it. But this, without knowing what kind of pattern is applied, the warden, the supervising element, is not able to extract the data. So you need this kind of knowledge where information is hidden. You need the regular data that looks normal, and you need the embedded data to retrieve on both sides. So what kind of approaches did we had a look at? Let me just see. We had this overview on the various approaches. It's always good to structure related work and overview on existing solutions in such a tree structure. That's very, very convenient, because typically you have here many examples how this is implemented, and you have here many examples. So there's many examples in general, and if you want to structure related work, then typically it's quite good to try to create this kind of boxes, not too many, in which the solutions fall. So on the one side we have timing patterns, where it's basically important when you send a message, or if you send a message, which could be also somehow related to time, or what you send in the message. So for example, this timing patterns, the information is carried, if it's totally protocol agnostic, then either in the differences in this interpacket times, so how much gaps you leave between the packet, or message timing when you send a packet at specific, let's say you agree with your recipient that if you send a message at exact full seconds, then it is a 0, and if you send it at half seconds, then it's a 1. Somehow you can agree on the pattern. Or the throughput rate, how many packets per second you send. This is all related to timing, and it does not modify any kind of structure. It does not leave out any messages. It does not reorder them. They are sent in the same order. No messages left out, but just the time is modified. So, and then we had a look at the protocol-aware protocols. Here the main idea was that you know that some protocols are in place which retransmit if the messages are lost. One moment. Kurz schauen. Okay. So that where you are aware that messages are retransmitted, so if you use TCP, and TCP makes sure that if a packet has been lost, it is resent. So if you send 134 and somehow the counterpart notices 2 is missing, then you can resend 2. But what you can also do is, just if 2 has not been missing, you send it just twice by faking that you just missed the acknowledgement. That you can also do, or you change the order of the packets because you know that TCP will correct it. Or this starting basically with the frame collisions. This is more on the lower layers. In case that you are using some wireless protocol where only one participant can send, and otherwise it comes to a collision at the recipient side, typically then you can initiate these kind of collisions and enforce a retransmission. That doesn't mean that it's your own packet that is that you break your own packet, but you could also hijack, or basically you can have a look who else is communicating, and if you are sending a packet at the right time, then you are stopping them. You are creating a collision for their packets, but the recipient can also detect this. The temperature was a little bit off. So this is if a server is overloaded, then it behaves a little bit differently, has longer response times, and if the sender interacts with a server to cause stress, and the recipient interacts with the server to observe how much stress is there, also by sending some random queries and seeing whether the replies are delayed or not. So this does not change anything about the content of the message. It's just the order. It's just whether they are resent or not. So this is also not taking influence on specific contents of the message. So these are all just timing patterns. And now today we will look into this storage patterns to have a look what can you modify in the data packets itself without modifying or changing their behavior. Yes, so here we are now, and let's have first a look at the structure of packets that are modified. So here it's written size modulation, sequence, and adding redundancy. So now think of any kind of protocol that has a header. You can maybe think of an HTTP protocol which sends out a query to download a website. And typically, yeah, let's do it. Let's have a look at, I'm quite sure the example will also come, but let's have a look at how an HTTP protocol looks like. Let's observe all of it. Okay, great. So here we have the request for, this should be for Graffi.de, yes, exactly. And you see there's not just a request for Graffi.de, but it's also telling that I'm using Mozilla 5.0 Windows, Gecko, Firefox 139. I accept this kind of data files. These languages, this encoding, this connection type, priority maybe. So you see there's not just a minimum request that is required, asking for the website, but there's also some additional information. And now we are about structure modifying steganography. And the structure is not about individual values, but the order in which these these additional information come. This you can also transfer to other protocols which have a header and optional fields. So all of these fields, user agent, accept language, accept encoding, they are optional. I mean, we could also leave them out. And this is also something that I think we did with the proxy, where you could modify and leave out this kind of details, or you could modify these details. But these are optional fields. And the structure is in which order these fields come and which fields are there at all. So let's have a look at what elements we have. So let's start with the size modulation pattern. So if there is an option to, it's written the size of the header, just let's say this HTTP request, how many entries you have, this is also somehow reflecting the size. But you can also do it at lower layers when you specify the length of the message. Also in the header, you can just add more length to it without real data. So what you could do is, as an example, just adapt the length of your messages if you have the ability to, and encode the information in this pattern. What you can also do is, for example, IP supports the fragmentation of files. Let's have a look at Wireshark. So if you look into here the IP header, then we can basically decide whether we want to fragment the packet or not. Even if it's not needed, we could, for example, create split up this single request, which is how large? 400 bytes, 398 bytes on the wire. We could still decide to split it up in 2 individual packets, and by this, although it's not necessary, we modify the structure and encode the information in this. So this could be an example how you modify the structure. You do not change the entries, the values that has been transmitted. You just take influence on how the packets look like. This is the example that I wanted to show you based on the HTTP optional fields. So what you could do is to change the sequence of header other elements to encode hidden information. So especially when you have an optional set of values, you can reorder them. It is interpreted the same way by the recipient. The recipient takes the message and goes through the list and then checks whether optional elements are set, but the order is ignored. But the recipient of the steganographic message can interpret it as some kind of hidden information. So here, for example, you can just simply exchange the order, but there's also other elements where you can, other protocols where you can make use of it, especially if you have the ability to have this kind of optional headers. Okay. Yeah, and for the regular recipient, this is really not visible because they just process individually each optional field, and maybe they set the browser and then they set the language, but in the code for the processing doesn't make a difference whether you first assign value variable A or variable B. What you can also do is to add unnecessary elements. So it's written, the covered channel creates new space within a given header element to hide data in it. So it's not really needed. It's a new field that you can, for example, use to signal some kind of information. So you can say if this element is present, then this is signaling some kind of information, and if it's not present, then another, so it's 1 or 0 is signaled. You can also you can basically, so while in the previous examples it was reordering, now it's adding more elements which are not needed. It's a little bit different because it really then depends on the protocol, how well it deals with new optional fields. It's a little bit different because now you add new data in contrast to the previous one where you didn't add new data, you just modified the old one in its order. Yeah, it can be questionable whether this is really just a structure modifying, not value modifying, but okay, let's accept this. Okay, so this was about structure modifying, and now it's about the structure is preserved, but the values are modified. So what we want to do now is to basically look into the code, look into the protocols and see if we do not modify the structure, so the order of the header fields or adding new fields which are not really needed, which of the values that are anyway transmitted can we modify without harming the protocol. And typically, so you need to be able to change the data without having effect. And one example for that is to modify the random values that you can select. So sometimes in protocols you can select a random value. For example, the IP version 4 identifier field, or the initial sequence number, or some kind of identifier field which you can select. let's have a look. So what did we have here? Let's get the first one. Here you have the identification value. This is the important element is here that together with the fragments you can identify which of the fragments are belonging together. This is the main purpose. So if a packet has been split up in smaller parts because the individual transmission at the lower layers is requiring that the segments are smaller, okay, then you still have to identify that they belong together. This is the identification field. And there's no real other need for this. So if let's have a look. So if we go through it, where I'll get, is there some pattern? There doesn't seem to be any pattern here. So you can choose it somehow by random, and by choosing by random, if you can choose something by random, then you can embed some information in it. For example, you can say that the last 2 bits of this random number are the information that you want to transfer. Yes, another element where we have this is in TCP, when we have TCP, do we have SYN? Okay. Let's have a look at TCP. Is there some connection establishment here? Well, so in TCP, what you also have is that when you establish the when you set up the 3-way handshake, but I would like to see whether, do we have some SYN? TCP flag, I think, flag SYN. Yeah. Okay, so this should be some kind of network establishment. Do we have it somewhere? Doesn't matter, I don't want to go into detail. Basically what you say is, in order to not lose a data packet, you have to first set up this handshake. So we need actually, it doesn't matter. So basically you have to set up, you have to announce that you want to communicate now, and you will start numbering your bytes starting with this sequence number. But this sequence number, that's basically not starting at 0, but at some random value, you can choose by your own will, and there you can also embed some information. You can also say, I don't know, the last 2 bits or the last 4 bits are the relevant information that you want to communicate. Later, for the next packets, you are bound to this number, so you cannot really embed new information. But for the first initial setup of the communication, you can use this freedom to select your sequence number and embed some information. So, in summary, every time you have a random value, you can embed some information in it, and it's very difficult, of course, for the warden, for the supervising component to identify a pattern in that, because you can say the first, 7th, and 9th bit encodes the information, and you have to first, I don't know, XOR it with some specific key. So it's really difficult to identify that these bits are relevant. What you can also do is some packets require a specific length. And especially if it's about encoding, let's say, then typically, okay, so so in some of the packets, some of the link layer elements where you have fixed sizes, what time you have to send your data, because it's wireless and time, there are time slots and so on. So you sometimes have to fill up the free space in order to complete the length of your mandatory length of your header. So sometimes there are bits that are unused, so they are also announced, maybe either by unused bit count or somehow by specifying the length of the packet, and after that is the padding. So, and you can now insert in these fields basically your hidden information, because everything that is padding that is announced to not be used is not interpreted by the protocol stack. So typically any kind of regular user would not look at these bytes, But if you know there's some information hidden, you can basically look into it and analyze it. Also in IP version 4, there are some, such as the don't fragment flag that's maybe ignored, or the reserved flags, or other unused bits in the IP encapsulation if we are having some tunneling. So these are some free spaces that you can use to hide information in it. It's quite interesting. There are also very similar examples for file systems. Do you know some file systems, some steganographic file systems that hide information in the unused elements, in unused fields? So, for example, there has been a TrueCrypt, which has been now, they have mysteriously closed, and they have recommended BitLocker by Microsoft. So there was a discussion whether it is legit or not. But now, for example, VeraCrypt is a tool where you have typically your file system, you have typically some kind of information on the structure, and it tells basically where the files are located on your hard disk. Yet typically, you have this kind of overview, meta information that tells where files are, where folders are, and if you've once done some kind of, I'm not sure whether it's still needed, some defragmentation, then you see which fields of the hard disk are unused. Have you seen some kind of images for that? So very generally how file systems work, you have some kind of structure and it points, here's a file named so-and-so, and it starts here, ends there. And the same for folders, the same for files, and the rest is unused. And typically, where you can also hide files is, such as VeraCrypt is doing, you can create a new file system here. It looks random. Of course, there's some key, it's encrypted, so that everything here looks random, but here's a new structure that tells, okay, here is a file, and here's a file, and here's a file. And you can plausibly deny that something is there. So if law enforcement or whoever forces you to reveal that you have hidden some files, you can plausibly deny that there's nothing, because all of these bits look random. It's encrypted by some key that you have to memorize. But if you know the key, you can unlock the structure, unlock the files, and by using the keys that are somewhere stored, also encrypted, you can access the files. Of course, what could happen, yeah?
So even if they search in the unused space, they still wouldn't find it?
Exactly, yes.
Okay.
So because, I mean, the goal of some encryption mechanisms is that to scramble the data, that all zeros and ones are equally probable. So it looks really random. And if you don't know the key, you don't see you cannot recreate the structure. And in the structure, probably there's some further keys stored by which these files are here accessible. But the structure knows where the files are in the unused space. The only bad thing that can happen, if you fill your regular hard disk, then also this space is used for files, and this space, and then over time you could overwrite your hidden partition, but that's up to you. And very similarly here, so there are these unused fields, and if you know what's inside and how to decrypt it, then you can make use of it, and if you don't know, then it just looks random to you. Okay, some very nice element that you can also make use of is in some protocols, the case, whether it's large or small letters, doesn't play a role, yeah? Because maybe internally, if you get some kind of optional header, then it just, and then some field, it's just maybe converted to lowercase and mapped to some internal list of potential parameters that you can specify. Yeah, and if you write user agent in this style or in that style, it doesn't make any difference, because the recipient typically would just convert it to lowercase. But if you don't convert it to lowercase because you know that there's some information hidden, then you can, of course, as you see, by selecting large or small letters, you can embed your information. And especially very old protocols such as HTTP, DNS, SMTP that have been invented in the 80s, where people still had to type in their terminal. So they are based on text interaction with real users. They accept some strings in this type, and then you can embed your information really by selecting the cases. And of course, it depends very much on the protocol, what kind of fields they accept, whether they have this separation depending on the case or not. But the old protocols typically ignore the cases. And this is a nice example because you modify the values, you keep the structure. So here you do not change the order or so, you just modify the values. But for a regular user, there's no effect. Okay. What you can also use, so this is HTTP, what you can also use is, so in very generic description is if you have n options to select from for a regular and valid interaction, depending on what you select out of the n values, you make a statement that can be interpreted as information. So what you could also do is if for, let's say you want, where can you embed this value modulation as well? So you have n values, which one do you select? Here you have the values small u or large u, but you can also have, let's say you have several DNS servers, 888 or 8844, and sometimes you use this, sometimes you use that. And depending on in which pattern you use these different DNS servers to request some URL, and the corresponding IP address you are sending to someone on the path of your DNS request some message. Also, if you take influence on the time to live or hop limit, so if you send out messages, then your IP addresses also contain a time to live. Let's have a look. Time to live 128, quite large, okay. So that means there are 128 possible hops to go before the message is dying, and basically you get it's not forward anymore, and you get a error message, ICMP error message, that the maximum hop time to live. So that time to live has reached 0. Okay, but you don't have to take 128. You could also start with 100 or with 100 or 90 or 80 or 70 or 73, and depending on, let's say, in which region you select the value, you could communicate some information. So how could this be made use of? So okay. So let's say you are the sender, and you have here several hops until you get to the router, and then it goes to the internet. And let's say this one is your recipient. Ist richtig geschrieben? Naja, okay. So, and let's say if you select time to live in the bracket of 101 to 120, then it's one specific bit pattern that you want to send, and I mean you can somehow you see that you have an option of different values you can select from. They do not take any influence on the behavior of the protocol. Maybe you just need 20 hops to this, so you have plenty of values that you can experiment with without risking that the packet gets not delivered. Okay. So to summarize first, so the timing patterns, very nice. It's just about when you send, and then we had that the very simple ones where you do not assume that packets are resent, where you do not assume that wrong orders are corrected. Here you have this retransmission element, you have loss, you have reordering, you have retransmission again, the frame collision. That was nice. Then now we are looking into the structure. It's basically the sequence and the redundancy of optional headers. So where you place them, whether you place them or not. And here you have typically the modification of random values or putting data in unused elements, unused fields, or to modify values in a way where it doesn't make any difference. There was also least significant bit. Let's go back. These are some sub-patterns. The case modification we had as an example, but there's also the least significant bit. That means if it's not a random value, but it has to be somehow accurate, such as if you have a timestamp, then still you can modify the lowest bit that has the least influence, and whether it's odd or even, you can embed some information. It's very similar to also the steganography with images, where you basically have RBG or RGB values that can be 0 to 255, and whether the redness is 128 or 127, it's not really visible, so you modify the last bit. And the same is also for any kind of protocol where you have something like timestamp. It should be pretty accurate, but it doesn't have to be 100% accurate. Yes?
What's the practical application of now knowing how one can hide information in the communication?
What's the practical
Application for it? And why do we learn this?
Oh, okay, yeah, because typically in companies, one of the main goal is that so just to repeat the question, why is that relevant in industry, for example? Because companies are very highly interested in not losing their data, so their secrets and so on. And typically you get very restricted devices, how you can communicate, what you can do. And there are many possibilities to retrieve data still out of the company by using such kind of methods. So the question is, because once you are in a company, and depending on how large the company is, the larger the company is, the more such potential information loss is an issue. In smaller companies it's less an issue because you cannot invest too much time in it or too much money. But in bigger companies this is really an issue where you are highly restricted, and typically if you follow the news, then there are still some kind of domains where industry espionage is an issue, and this is one of the main applications of steganography, to really get data out of the companies by such means. Otherwise, the other element is to identify not just that the use case is industry espionage, but as we saw, another approach is also that, where is it? The applications. Yes, that you have malware hiding communication by this. So if you have some kind of some malware on your system that tries to get some commands, this is some way where to look at as well. So let's assume you have a maldoc, a malicious document. Yeah, I mean, if it tries to communicate to some server, and you know which common patterns to look for, also the malware providers will try at one point to adapt, because obviously if they follow the old paths, they will be detected. So they will also try to hide some kind of communication patterns, so that you should be aware what kind of strategies the attackers could do in order to counteract as well. Yeah. And what you could do, the question is where to embed it. And one of the embedding elements is either to to extend the intrusion detection systems. It's questionable. So, for example, you could look for any kind of strange. So, by knowing all these elements, then you could start thinking, okay, how do I, let's say, address the issue of the time agnostic pattern? So, where you just take influence on when the packets are sent. What would you do? So then you can think of strategies. How can you counteract or stop this kind of communication channels? Yeah.
Because for me it seems like a lot and like almost impossible to detect something like this if you don't know where to look for it. Since you can also combine these, and if you embed information, then you can also encrypt it. And then how can you ever detect it?
Yeah, that's a good question, but there are some ways. So, for example, the protocol agnostic that take influence on the time. A typical approach would be to, so let's say if we would add in proxy here, that you can communicate, that you have to communicate with, then all of the retransmissions, artificial loss, message ordering is happening with the proxy. So this is Alice who wants to communicate with Bob, but you add a proxy, then all of the loss is compensated here, and then just the proxy communicates with B. And then basically artificial loss doesn't work, message ordering doesn't work, retransmission doesn't work, frame collisions do not work, temperature, maybe, I'm not, because that's somehow indirect. Okay, that would be an element. Then the protocol agnostic. The proxy could also either, let's say so typically, if you have some kind of variance in the timing patterns, what can you do? There you use a leaky bucket. Have you heard that before? A bucket with a hole? Okay. So the idea is you have a bucket. So now and there are different kind of streams coming in. Sometimes some drops, sometimes some streams. But the bucket only has a fixed output stream. And here you have a dynamic input stream. Of course, this is not a bucket. This is some kind of network controller where you take in at various speeds the data, but you only let it out at fixed output stream. So basically, there you cannot apply some kind of timing pattern because you do not control anymore how the packets will go out. So if this is often done in multimedia, for example, when you have some bursts of traffic and then something for some time again, no traffic, then you typically control the continuous data stream by assigning some kind of virtual money for every packet. And in order to send out a new packet, you need to accumulate some amount of tokens, some amount of virtual money, and every second you get an amount of virtual money, so some tokens. So typically, by this you can take control that the output stream is continuous. So for example, if we had previously these, let's go back, this kind of interactions, this gaps, if you send it to the proxy and the proxy sends it out at a fixed rate, ignoring your previous times, then you've lost the information. If the throughput you send to the proxy at a specific rate, but the proxy sends it out as a fixed rate, the information is also filtered away. What else did you have? Message timing, that as well. I mean, if the acknowledgements, so typically, one of the approaches, you don't have to detect it, you just apply some kind of filter that takes away lots of the kind of variability. So you try to make it very homogeneous. One moment. Oh, Canada. Okay, so that would be some counter example how to do it. So either to use a proxy and that companies also do. They really use some proxies that you have to go through, and then you're also somehow concerned, what else do they observe? Because they really do not. You cannot also use USB sticks, for example. You cannot take your machine at home. So there are many constraints that apply when you are working at the company that has some secrets that are very protected. What else did we had? Message ordering. That's also something that you can correct with a proxy. So if you put an entity in between that reorders all information in the correct order before sending it out to the real internet, retransmissions are also corrected. So this is something that is easy to apply with a proxy that just flattens out the interaction curve. What else do we have? Just to summarize, so this is for you will face this depending on which company you will work on. Okay, final element. What else can be modified? So there we do not go too much into detail because this is now really modifying the payload. There we can add any kind of encrypted information. So this is not too much network related, so all elements before were somehow network related. Either it's about the timing or the order of headers or the unused or random parts of the headers. But if you modify the payload, then this is not anymore network steganography. It's about what kind of data you send. You could also send some kind of images where the bits of the colors are reflecting the information. Okay. What else can be done, but this is just some kind of last example, is that you do not embed all of your information in one protocol, but you embed it in various protocols. So let's say you have some kind of HTTP protocol where you send one part of the information, then you have some ICMP protocol which embeds some other information, so that you split it among various protocols, in the assumption that, let's say, if there's a strong focus on one kind of protocol, HTTP for example, then they get only a fraction of the data that you wanted to send and not all of it. And it's more difficult to identify that there's some kind of pattern going on. What you can also do, it depends how you use these various protocols. Either you hop from, so you use different protocols, or you could also modify or hop from pattern to pattern. So sometimes you use timing information, sometimes you modify the order of the header fields, sometimes you modify the sequence number in the TCP handshake that you can also apply. Of course, this is getting more and more difficult than to detect, but still, because it's not, so detecting is really difficult, but what you can do is to remove all of the variants in the traffic by maybe using really a proxy to filter and to recreate every packet anew with only the really required information, and everything that can be used as some kind of information hiding element to remove. Okay. Yes, I think in the one of the previous lab exercise already had this tool in use. Is it right? I'm not really sure. One moment. As an example how this can be utilized and to experiment with it, there's this covered channel education analysis protocol. So it's basically a protocol or a program that enables to modify various of the sending parameters in order to emulate this steganographic communication pattern. So what you can easily modify, so there's a server listening to incoming messages and displays what's happening, what packets have been received, and a client that is able to modulate and to influence the traffic to the server. You can modify the inter-arrival times to add some artificial loss and retransmission. And you can download it here. This is some professor from, is he from Worms? I think so, not really sure. Let me just, yeah. So basically he's also a professor in applied sciences, also in security, and he built this kind of tool. You can start a server listening to some port 8000. You can also have a look that you can send a HTTP1 request to it. You can send a HTTP 1.1 request to it, and then the server will show that these kind of requests have been received. And one element that you can do by hand, so this is not yet related to the program, is, for example, to this is just Python and curl, so just to interact with the server, you could send some header fields, some fields describing your browser with different casing that you can already see at the recipient server side that this kind of information is really received, and you can embed the information in it. But the tool can do more, so it's really allows you to modify various elements. So here on the right side you see the server. So the server is then started. White on black, great. And then you have the various requests. So just to stop it a little bit. What do we have here? Here we have the different calls for HTTP 1.0, 1.1, and then 1.0 again. And you have the various case settings for this field. And on the right side, what should happen is when we execute it, so now the server has started, if we execute the program, then over time the 6 requests should come in. Okay, so now we started it, and on the right side you can see that the 6 requests came in with according to the various header protocols, HTTP 1.0 and 1.1. And if we look into the packets in Wireshark, then we see that the user agent case really changes according to what we specified. Okay, what else can we do? So here we have a help. One moment. So where was it? Here. So here we can display what the client can do. So for example, we can specify destination to connect to. So up to now it was just Python and curl to access the web server, nothing special. But now with this tool, we can, for example, modify the inter-arrival times of the packets. We can specify the number of packets to send, the initial sequence number to embed some information. What else? Predefined sequence number that might also be wrong, so that we can modify basically the order of the packets. We can add duplicates. We can exclude packets with specific sequence numbers, so to drop them, to have this artificial loss. And if we start now the client with to connect to the web server at port 8000, send 5 packets and exclude the second packet out of the 5, then this is then this is what should happen. Let's one moment. So what we expect now is that we get the list of 1, 3, 4, 5. And then we get the packets 1, 3, 4, 5. You see the second element should be seen. A moment, a little bit back. Yes. So here's 1, there's 3, there's 4, and there's 5. And we can also take, so basically the packet number 2 that should have arrived at, so packet 1 comes at second 0, packet 2 should come at second 1, and packet 3 at second 2. So just at that position of packet 2, there's a gap now. Yeah, I think for the next recordings I should really learn to have black text on white background. There should be now a duplicate packet. Which one should be? I'm not sure. So what are we doing now? So now we are setting the client to communicate still with the server. There should be 10 packets with this timings of the 100 milliseconds, 300, 300, 100, and you see there's a pattern in which the packets should be sent. And if you apply this, then the messages will now be sent. I stop it again. Here you have also the inter-packet time, so it starts first at 0 seconds, then after 100 milliseconds, after 300, after 301, and after 100. So that's what we specified as a pattern. So it was not quite accurate, not exactly 300, but 301 milliseconds, that's okay. And if you look at the Wireshark timings here, you see as well, so there's at the time of 0 seconds, of 100 seconds, then plus 300, plus 300, plus 100, 100, 100, 300, 100. So it's according to the pattern that we specified. And yeah, I think that's it. So you can see that it's really not too complicated to embed this kind of information. And there's also lots of research on this. So also I had a colleague once who did his PhD on covert channels, how malicious nodes can communicate over various sensors in machines. So it's not just our network protocols. So for example, I think I brought the example that, for example, if you have an app on your smartphone, by measuring, by taking access to the gyroscope, you can identify which websites, so gyroscope as well as the load of the CPU, you can observe which kind of websites are opened at what times. Because Facebook has a different load pattern than something else, and using the gyroscope and some audio element, you could also, if you have a compliant notebook, you could also try to communicate and noticing and basically sending out information without by using different kind of channels. Let me just see, is that an example? Okay, so here's the example how the simple countermeasures can be applied as we talked about it. That's a very simple approach. Of course, you can do it more cleverly, but a very simple approach is to create some kind of normalization. So any kind of timing issues, any kind of special header fields where you choose randomly your values, you can apply some rules that your proxy, whatever you apply in this middle, recalculates the padding fields, that they all are set to 0, all optional fields are set to 0, all cases are normalized. That can be applied. And by adding it to a buffer with a dynamic addition, and here it is a static or somehow fixed performance, you can take away all of these timing elements. And this is also done in companies. So if you want to consult a company in terms of malware avoidance, of system hardening, then one element of network hardening, let's say, would also be to pipe all traffic to some kind of proxy that normalizes the traffic and eliminates, not just observes what in the traffic is transferred, so intrusion detection, but also to normalize the traffic at the cost of some delay. Okay, to summarize, so this is steganography hiding information and hiding messages in some kind of communication. You have very simple elements where you just modify the timings, such as inter-arrival time, appearance of messages or not. You have this protocol agnostic elements where you just modify the times, but you leave every packet intact in the same order. Or if you know that there will be some reordering, there will be some retransmission, then you can also omit messages, reorder. This is one element. And then you have the storage patterns. Typically you have then the structure modifying, where you just change the order of the header, if you modify the length of the packets, but do not add or delete other fields. And then you have the value modulation, where you basically modify all of the elements that are free for you to modify. Any kind of random value, new initial sequence number, new identification numbers for the IP packets. That's what you can also do. Simple to implement is if you want to secure some networks, then this is some element that you need to address. Hard to detect, therefore it's not even about detection, it's about just removing the option to do so by eliminating all kind of options at the end. And where is it used? Data exfiltration, espionage, so industry espionage, if you want to get some secrets. Of course, military elements are also relevant there, but also in companies, if you want to exfiltrate some kind of patentable data. Concealed hidden communication, sometimes in countries with oppressing surveillance. I don't know, you can think of any kind of political conflict where people want to communicate to the outside world without being detected, and malware command and control. Okay, great. Good. A little bit late. Okay, so let's start with the next lecture on malware. Maybe you should also give a short element on your paper that you had. So, one moment. Okay, so let's start with malware. We look now at different kind of examples. That's of course still everywhere an ongoing plethora of options. You just want to see what kind of prominent elements and attacks they have been, and what to learn from them. But actually from every kind of malware we can learn something. So let's have a look. 20 years ago there was some simple UDP packet that was sent out, and after that large parts of the internet were not reachable. So what happened? That was the so-called SQL slammer, which led to a dramatic overload across the internet. Emergency calls was not working, airline tickets were not working, lots of money has been, lots of damages have been caused. So a simple UDP packet, one single simple UDP packet. So what has happened? So there has been first one single packet, let's say, and after a short time there has been some explosion of these kind of packets sent back and forth across the internet. So let's have a look what was happening. And one of the core elements is that there has been a vulnerability in the Microsoft SQL Server 2000. Of course, this is outdated, but something to learn from it. And that was a directory service, where you could search for databases on a network. And there it was offering a port 1434, which is accessible by UDP. And the first byte in the packet determines the request type. Okay. For example, 04 as a search for a database whose name is given by maximum 10 bytes. And then a null terminated string, so the 10 bytes. Then there's some kind of null. So to make it clear, so there's first this null 04, then come 10 bytes, and then there's a termination string, so null termination. Basically to say this is where the string ends, so if you don't use the full 10 bytes, use just 7 bytes, then the 8th byte would be the 0, and then you can identify, okay, I don't have to read the remaining 1-2 bytes, or how many. So basically, it was expecting that the request is formatted according to this. And then it takes the string, assembles it with 2 other strings of constant length, and there's a total of 128 bytes reserved on the stack for this purpose. So I hope you get it. So you get basically the request, then it takes the string. So let's say this is our string that we are looking for. So it identifies, okay, there's a request coming in. So I should write this string on the stack. So here's my stack. I have 100, make it different, let's say. So I have 128 bytes for this reserved. So I put the string here. Then I have another string, another string of constant length. And then my program will go through it and process this area of memory and analyze where the selected database is. So what can go wrong? What can go wrong? In the SQL server, you have a set of other potential requests, and they are all numbered so that the recipient, the server, knows what kind of request it is. Is 04 somehow critical? Not really. So then comes the string, and it can have let's say 1 byte to 10 bytes. You don't know how long it takes. Yeah. But you know when it will stop is when there's basically a null byte coming. Then you know, okay, this is where the string ends. So it can be 1 byte, I don't know. And then there comes the 00. Or I don't know, there are 9 bytes or 10 bytes, and then here's the end of the string. So, and then depending, so if you have here 9 bytes, you take these 9 bytes, and this is the stack, and you reserved 128 bytes. You put the bytes on the stack. It's a little bit, let's make it with 32 words. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So and then you add some, I don't know, further information. So here's then A, so your other string, and then there's B. Okay, and then you basically know, okay, yeah, probably it will not split in the middle, but okay. And this is empty. What can go wrong in this setup? Yes, Stack Overflow. So what happens if you send 100 bytes? Yeah, it just accepts the string because it accepts that it's null terminated. Is there a real identification or some kind of assessment that you did not get more than 10 bytes? Yeah, that's the problem. Because if you get more bytes than 10, then you just fill it up. And at some point you will get up here and you overwrote some previous values. And the question is, what kind of of values can you overwrite? So it's not checked whether the UDP packet is only 10 bytes long. So that's the core problem, because it was allowed for the user to specify when its input ends, and whether it really ends there, it has not been verified. So let's see, what does it do? So first, okay, it starts with 04, then it contains fill bytes and the machine code of the worm. So what does it send? It will send, okay, the 04, okay, this is not critical, but then it tries to fill up these 128 bytes with something, and then there's here the code of the worm. and there's no null byte, so that the whole worm is accepted as input. So that it just fills the whole space, so there's no termination at all. So what is the code of the worm? It just randomly calculates 32 bits. This will be then interpreted as IP address, and the worm sends itself to this IP address as a UDP packet. And what does it send? It sends this part that is basically taken as an input to fill. So basically, if it sends itself from here to here, and at the other side, and this 04 should also be added at the front, so that the recipient takes, okay, there's a request, there's a 04, and now I fill my buffer with the same bits that have been in the buffer of the other machine, and there's the code of the worm, and then I start executing the same process. So the question is, if we exceed this 128 bytes, why is this part started to be executed? So why is it executed and not treated as some kind of variable that we received? There we will have an example. And basically, we need to learn a little bit about the buffer management and what kind of information is stored there. Let me just see at what point do we have this? Here at last. Okay. So let's have a first look. Why is it effective? So typically, if you have a method that accepts some data that's executed. So typically, if you create a method, then it looks, okay, I need to reserve some space for variables. So this will be, for example, this 128 bytes that you have to first specify. And then there's some kind of callback at one point, so not callback, but a return address, which specifies once the method is completed, to which address of execution should we return back. So typically there's then some so how is the traffic flows? You have listened to Rechenarchitektur. I think one of the examples is that what we discussed there. So you typically have your program counter, you process the instructions one by one, and if you have a method call, then you would jump with your program counter to the new address of the method that you are calling. But of course, then you want to go back to the same position, basically so here's call method. Here's the method that you want to call, and then you want to continue with the next instruction. Yeah. So for example, what do we have here? That's these. That's it. Okay, let's go. Oh, let's draw in this one. So let's have a simple method. So a equals b. Sorry, not b, equals 5. 5, b equals 6. C equals sum of a and b, and print c. Yeah. So this is a sum method, which basically just calculates a plus b, but it assumes to have a and b as an input. And what typically is happening, so this is, let's say, having the address 1, 2, 3. This might be having the address in the main memory, I don't know, 7, 8, 9. So when this is called, so typically the program counter now goes through. So this is line or instruction 1 through 3, then 4 bytes more if you have a 32-bit system, 1 to 7. Okay, let's make it realistic. 1, 3, 2. And if this is called, then it's jumping It's basically what is happening here. So basically you have to memorize as a return address. We want to jump back then to the next address that we would have called, 136. This will be the return address. And I don't know, here for A and B you reserve 64 bits, for example. Okay. So, and what happens here, if basically a very similar thing was also done in the SQL Slammer, and now you try to fill up this space. If you fill up the return address and you end the method, this will be the address you jump to. So what you could do is to say, okay, let's, I don't know, I know my code will take 1024. So from here to there will be the addresses. Let's make it a little bit different. 0 to 124. So, and at this point I will assign address that will jump there. So by overwriting this part, this return method, I can specify, I don't know, this is of course just relative, so we don't know the exact address. So we say we want to jump to this position, which is here, and then execute the elements that we also filled here. So the data that we fill into this bit fields, so it's just 32 bits, let's say, will be interpreted as instruction. So this is the power of overwriting the return address. Then you can say at which position the bits should be interpreted as instructions and executed. Basically what the SQL Slammer did is to write here that create, so what did it do? It said random 32 bits, that should be an IP address. The recipient sent UDP packet consisting of this request statement, as well as the data from here to there. So I don't know, how much is it? It's R0 plus 124 plus 128, something like this. I mean, you can calculate basically from top here to there. This should be the bits that should be sent out. And the recipient will then have the same problem as we had, because it receives the 04 and then it writes all of this data to the top and will execute it because the return address is overwritten. So basically this is the core idea, how buffer overflow can benefit you and allow you to control what code is executed by taking influence on where the next execution, which instruction should be executed next. Yeah, that you can control by overwriting the return address. So that was that's the benefit of so the easy element about buffer overflows. And in this case, it was just one single UDP message. Why is UDP better than TCP? Because in UDP you just have to send out a message. You don't have any handshake. You just send it out to any random IP addresses that you want. And if there's a server at that point, it will have this buffer overflow. It will execute the code that you sent it, and it will spread again. So it basically, you first have one machine, then it spreads to n machines, then every of them spread to n machines. So you have at this point n to the square. Then you see it's really exponentially growing. Just small message, and it was benefiting from this homogeneous infrastructure. So there were quite many Windows, the Microsoft SQL Server 2000s available. All had the same vulnerability, and it was very effective through this. Okay, so let's have a look. So this is one example for buffer overflows. We will also have a look at other elements. But the core element at the end is that how programs are executed in machines. So one of the main purpose of the attackers will be to overwrite this specific return code, return address above the stack. So there's typically the stack, how much reserved for variables, including user input. And if the user is able, there's something else, but at one point there's some return address, and that's the magic. If the attacker will be able to rewrite, so the overflow goal, rewrite return address to memory part that you control. So for example, if you could modify the return address that it starts its next execution at this point, and this is the data that you gave as an input, then you can bring the system to execute the lines of code that you wrote here. So it's how you can initiate any kind of activity that you want. Okay, let's have a look at various malware types. We will not, of course, go into detail, but just what are the main common elements and how to differentiate. There's some overlap with IT security, I know, but we will also have a look at new elements. So, a virus. Have you any time run a virus on your machine? Did you have a virus once? No, never. That's good. At my time, that was a little bit different. So these are executables that are replicating themselves, and basically that's the main purpose. So how typically it was done, but as in malware, are there virus malware? Malware so affecting other Office documents? I'm not sure. So typically this is for executables where you have some kind of part of real code, I don't know, and one part, if you execute this software, then this virus part tries to identify other files that are not yet affected and copies itself over there so that it will be executed as well at one time. So basically, every time such a virus is executed, it looks for other files it can copy its part into without losing the feature and the function of the original file. But the next time this file is executed, it also scans other locations and looks for files it can affect. And if these files, executables, are somehow shared, then that spreads over various machines. So typically that was quite, that was at a time where really files were changed between individuals, where executables were changed between individuals, that either by CD-ROM or DVD or whatever. But now that we get typically all of the programs from the internet and don't have physical copies, that might have had a decline in usage of viruses. And what do we else do? So once, purpose number one is to spread from one file to other executables, ideally on some kind of hard disks, or to be sent via email or USB sticks, and then to be executed at new machines, and then do some harm, but it's optional. Doing harm is optional. Okay, and you don't need any large resources on your own as an attacker. It's quite interesting. You just create this part that attacks one file, and then it spreads itself and it's executed. I once also tried to write some virus for education purposes. But it's in a very simple programming language, and the goal was also exactly like this. So there was one program that, when executed, looked for files of the same type, should open them and add this virus code of looking for files and copying its side that was the goal, to copy its code into these other files. Yeah, so it opened every file, not just the files of the same type. Then I had to reinstall my operating system. So. But okay. So, but it's also interesting, yeah, how to program. I mean, what cat and mouse game there is basically. So, what additional purpose they might have. But the core element is that it spreads itself, it executes, it copies itself to other executables. And whether it has additional features and additional functionalities that are harmful, that is of lower category, so it's not really necessary. Okay, yeah. Nowadays, so how previously it has been written in assembler or other operating languages, depending on what kind of programs you want to affect. But typically in assembler, if you have machine code, and there's some virus part, it looks for other files and copies over this virus part. So that's also executed there. Nowadays there are some construction kits, there's also some industry supporting it. You can buy viruses, you can build them for your own purposes. There's some kind of professionalization ongoing. But the question is whether you yourself are really, or who's really affected, who is really worth of, what is the business model behind this. So typically you see it when you have this encrypting viruses that are encrypting all kind of, so this how is it called, where the files are encrypted and there's some ransomware. So it's ransomware, so where there's some ransom asked for, so all of the files are encrypted, and if you want your data back, then pay us some money. This is some business model that typically drives the development of this kind of viruses as well. So what should be done very simply against viruses? Or let's say you are a University of Applied Sciences, what should they do to have less risk from viruses? So let's say the potential attack is that all of the data is encrypted and they want money for it. What would you do? Nothing? So give up? No, I mean, yeah, there of course are different options. So very importantly, have backups. That's for sure. It sounds easy, but often it's not done. But okay, next time we will have more. We will look more into detail into this. Also, antivirus software, how they identify viruses, what viruses do to not be identified, and what antiviruses then can again do to detect that evading of detection. Okay, nice that you have been here today. So see you then next time.